Welcome back to Notes for Engineers. I'm Alistair Cook, and I'm very pleased to be joined again by Michael Webster. What have you got for us today, Michael?
So today, Alistair, we're going to talk about virtualizing SQL Server databases, which is something I've just released a book upon with VMware, and how it works in the traditional storage architectures and how Nutanix architecture can make it much simpler without compromising performance or availability.
All right, so we should dig into the challenges that high I/O workloads like SQL give for a traditional storage array.
Absolutely. So one of the primary challenges with a traditional database platform, be it SQL Server, Oracle, or any other, is we have our virtual machine, and our virtual machine will have lots of individual disks and normally lots of controllers as well. So I'll draw 4 controllers.
And this is all about parallelizing up all of the different I/O types.
That's exactly right. So database is really just an extension of the storage underneath it. It's just a big cache, essentially, at the end of that storage, and it then uses the CPU and memory to do fast searches and everything like that. So now off each of these controllers, we'll have a number of virtual disks, and I'll just draw one just to make it easy.
But you can imagine that we can fan out to
Absolutely.
a dozen off each of those controllers.
Yeah, exactly. So if this is a SCSI controller, you can have 15 disks on each, so you can have 60 across the virtual machine. If you're using SATA controllers, then you can have more. But for high-performance workload, you really need to use SCSI. Now, every single component in this architecture has a queue depth. What we have, of course, on these disks is we have a number of files. And the way the database interacts with those files and the SCSI controllers and the queues determines what the performance can be. So if you've only got one file and one LUN, even if you've got the most powerful SQL Server in the world with the most memory and CPUs possible, it's going to get bottlenecked by that single file, because this SCSI controller here might only have a queue depth of 32, depending on the type of controller that you've got. But basically what happens is the pages of the database are read from the file in memory, and you can get lots of contention and locking on those pages in memory unless you spread it out. So that's one of the reasons why you spread out the data files and the transaction log and the tempDB across a number of different controllers, a number of different disks, is to reduce the contention in memory so that the database can get locked up and it doesn't even send I/O down to disk because it's locked up in memory. Now, the next thing you can run into is if you don't have enough queues, is the actual I/Os that do want to go down to disk get bottlenecked inside the operating system. And that means you can't even push the storage to its full capabilities. So every single controller has a particular queue depth, but every single virtual disk also has a particular queue depth. And this is why for databases where we need lots of queues, essentially to drive the parallelism of I/O, we need more disks, more controllers to be able to do that. Now, what happens, though, is if this is sitting on a traditional storage array...
We should say that this whole characteristic so far is exactly the same if you're still working in an old physical environment.
Absolutely.
There's nothing outside of the operating system behavior so far.
Exactly. That's 100% correct. So let's say this is a LUN, and we've gone ahead and we've zoned it and masked it and everything like that. And then we have our... we'll have our big storage array down here, and it's going to have 2 controllers, and we'll have our 2 fabric switches, for example, and we're going to have this sort of a setup here. So typical 2 controller setup where it's redundant and everything like that. Now, the queuing is a problem up here, but then as you add on more and more database service to the same LUN, you get exactly the same problem. So every LUN has a queue depth as well per host, and every LUN has a queue depth per storage processor. Now, if you overload anything in this chain, it's not just going to mean that the database goes slow, it can have catastrophic consequences to the actual performance of the entire array. And you get into a situation if you overload the queues where it says, hey, hang on a second, back off. And it will basically send you down to 1 outstanding I/O for the entire thing for that LUN. Or if you overload the storage processor, basically that whole storage processor is going to back off, and that's going to slow everything. Exactly.
Don't send me another I/O for 2 seconds.
Exactly, and it can get to the point where the storage processor completely freezes, and then times out at the host, which then puts you in an all paths down situation, and then you can get path thrashing going on. So depending on whether this is an active passive array or an active active array, will depend on how bad that situation gets. So the problem is these storage processes and the LUNs become a point of contention in a traditional storage architecture once you've got out of the database layout type thing. So best practices have multiple virtual SCSI adapters, multiple virtual disks, and make sure you've got enough and that the different I/O patterns are split out. Now, in a traditional architecture as well, we get this problem about having this single LUN here for these SQL Server databases. So
you're hitting a LUN queue and you really want to parallelize that and have multiple LUNs.
Exactly. So if you've got very high performance databases, you do need to have more LUNs, and you might actually split these virtual SCSI controllers up into individual LUNs and put the virtual disks on those different LUNs. Now, one of the benefits that has is that whatever that virtual disk's I/O pattern is going to be preserved through the LUN down to the storage processor.
Rather than blended all of the other.
Rather than blended. So, for example, if this is the transaction log over here, that's a sequential stream. It's normally a very large I/O size, so it'd be between 64 and 512 kilobytes per I/O, and it's just going to shoot that down to the array. Exactly. Now, if everything was on the one LUN, it's all going to come out of the array completely random, blended together. And if you haven't made sure that your virtual disks are aligned, you can get a lot of split IOs, and that can slow down the array very drastically depending on the type of storage system that you've got. In the worst case scenario, on some storage platforms, for your 100% storage investment, you can get 20% performance.
Ouch.
Yep, and it also depends on the type of RAID levels and things like that you're running, which can also have a massive impact on performance.
We better cover some of those in the tutorial pieces for those who didn't understand anything of what Michael just covered. We'll look at some more storage and tutorials.
That's right. So in a traditional architecture, to increase performance, you need more LUNs. More LUNs means you've got more things to manage. You can reduce the number of LUNs, but have a bigger queue depth, and that can be configured on the HBA. But why go to all this incredible complexity?
But there's also constraints about maximum number of LUNs and paths to storage for your exec server, which are very nasty if you push them.
That's right. And if you get over 100 LUNs on an ESX server, potentially things can slow down a little bit, depending on how you're accessing those LUNs as well. But there's also a lot of complexity in managing all of this back-end infrastructure. You've got to be able to zone and mask everything. You've got to manage each individual LUN. Your storage team doesn't get any visibility of what's actually happening at the virtual machine layer. It's quite a bit. It's quite a bit to troubleshoot and diagnose.
And I've seen some interesting discussions about how to scale these dual controller storage arrays, where you're adding different elements of
it's
array
very easy
to scale.
You just
buy another one.
You buy another one, and you double your management overhead. Which eventually you're either going to have to grow a very massive storage team, or you're going to have to work your storage admins 24/7. Now, of course, there are arrays that do scale out more. This is just a typical scenario where a lot of arrays are only two storage controllers.
Most of the arrays that we see running x86 server connected are just dual controller arrays. The higher number of controllers gets very expensive, and you mostly see them attached to mainframe class compute.
Yes, exactly. Now, there's no reason why we can't have the virtual machine and this idealized layout, and this can all be templated so that it's very quick and easy and efficient to deploy, but we can get rid of all of this back-end complexity. Now, the way that we do that,
you may not have known, but this is actually a giant post-it note.
Yep, so we can rip that off. Now, we can have our database server with its controllers, and we'll have our virtual disks. And our files on those disks. Right, and we can have that on a single NFS data store with NDFS under the top, below it.
That's Nutanix distributed file system.
Exactly. Now, basically, on a per host basis, the virtual machines access the local storage, SSDs and hard disks. So that means they got access to the local physical controllers' queue depths, and we don't have the same limits on the queuing as we do in a traditional architecture. What this also means is as I add another physical host, it all just grows out.
So you kind of get a controller per node. Every time you add a physical server, you get another controller for your storage array.
Exactly. So let's pretend for a second I've got a whole bunch of physical Nutanix nodes here. And so we've got 5 in total. So we've actually got 5 storage controllers in this environment. So every time we add a new host, we add a new controller. Now we start off with 3 hosts, and you can just grow one at a time. But what this also means is we don't run into storage processor queuing limitations across all the hosts at the same time, so affecting the performance.
We had multiple ESX servers fanning into one pair of controllers in the legacy architecture, whereas
That's
here,
correct.
each ESX server gets its own dedicated storage controller.
That's right. So it also means if the impact of losing a controller is much less. We've lost only 20% of our controllers versus losing 50% of our controllers before. It also means if for some reason we have a very, like a short spike in performance on one controller or one host, it's going to be limited to the impact of that host or controller as well. So this architecture is very much built to scale out, and it's very much built to run lots and lots and lots of virtual machines at the same time in parallel. What it's not built to do is run the biggest, hugest, monstrous virtual machines all on the same host.
So this goes with that idea that we had that made virtualization very attractive to DBAs, which is make lots and lots of database servers rather than one monster database server full of every resource you can buy.
Yep.
You build lots of them, and then operationally for the DBAs, their updates cycles, they can update individual machines, we can patch individual machines, and they like the operational benefits from that, let alone the infrastructural benefits we get.
Now, the major benefit to this is that we only need to worry about the layout of the virtual machine. All of this stuff under the covers is all taken care of. Because the storage I/O is local to the host where the virtual machine lives, it gets access to local host resources of the SSDs and the hard disks directly. It's only the writes that need to go over the network to be protected, and that's synchronously written. So you've always got the data protected throughout the entire cluster. And another advantage is you can basically add a new node. Say if there's a new version of something, hardware that comes out, all of these nodes can interoperate, so you're not restricted to waiting to a 3-year or 5-year refresh cycle to take advantage of the newest thing to improve the performance of the database. But we get away from all of the queuing complexities that we've had before. We don't have any zoning or masking or LUNs or anything like that to worry about. So this guy here can basically grow up to the maximum size that you can put while hosting 2,048 virtual machines, which is a vSphere limitation to how many virtual machines you can have on a single data store.
And that would typically be a pretty large number for even a large vSphere cluster to run 2,000 VMs.
And when you're talking about SQL Server databases, it's unlikely because most of these would be reasonable sized virtual machines. I mean, small database servers, probably 4 gigs of RAM, a CPU or 2.
But a production 64 gig database server, you're not going to run many of them per host.
No, exactly. So you might run 4 per host, in which case you'd run into 32 host limit per cluster from a vSphere host perspective. The Nutanix distributed file system, though, doesn't have any particular limits in terms of the number of hosts in a cluster.
It's not constrained the way the vSphere cluster is, although architecturally, would it be usual to align your Nutanix cluster to your vSphere cluster?
Normally, we would align it to top of rack.
Right.
So that we've got a failure domain being an entire rack. It depends how big your environment is, because that's a lot of virtual machines and everything like that. You can make the cluster smaller if you want to, but it actually gets faster and more resilient as you add more nodes. That's right. So if we have 20 2U boxes in a rack with a couple of top of rack switches, that's basically 400 terabytes of storage and about 20 terabytes of memory, 240 cores, 480 cores.
All in one 42
all in one rack. Yeah, exactly.
You're going to need a strong floor for that.
Yeah. Well, and you'd also need about 20 kilowatts of power to that rack as well, because each of the 2U boxes is about a kilowatt worth of power. So normally we see between 10 and 14 blocks, which is what we call a Nutanix block, which has either got 1, 2, or 4 nodes in it, and we can just scale these up linearly So the performance increases at the same time.
And you just add more nodes to get more capacity to run more VMs. And as you add nodes, you get capacity and performance all at the same time.
Now, lots of database administrators like to run either multiple instances or multiple schemas per database. There's no problem with that. There'll be a happy middle ground where it's better to scale out the number of database server VMs than it is to scale up the number of schemas per database server VM. Now, that's normally around manageability concerns, like if you've got lots of different business owners always arguing about when updates need to happen, or because you want to...
never happen.
Yeah, that's right. Or you want to more effectively, get performance resources so that, if you've got one schema in a converged database server that's using more performance than the others, it's going to affect the performance of those other schemas.
Because they're sharing the resources with one host.
Yeah. Whereas if you scale out the number of VMs, the hypervisor is much better at handling those types of constraints. And it really is just as easy as coming to the sort of service catalog for your databases, the 4 or 5 different types of database server that you want to have, creating templates for those, and then just rolling them out.
Quickly cutting them out.
Now, because we're also using local storage, we're not prone to the I/O blender effect. So if it's a sequential I/O stream like the transaction log we drew before, then it's just sequential. And if it's a random stream, we treat it as random. We also don't care whether it's split I/O or not split I/O. So we don't care if the I/Os are aligned, because our distributed file system handles all of that, and to the back-end storage, it is actually aligned anyway.
Realigns, right.
Yep.
To some of those magic stuff.
Exactly. So the biggest database servers that we're hosting at the moment, probably up to around 20,000 IOPS, and that would probably be on its own host, or any number of different sized database server VMs.
Up to that sort of scale.
But the individual host size itself can be 20 CPU cores and 512 gigs of memory as well.
Yeah, so that's a pretty serious machine.
Yep, exactly. So your unit of scale is still pretty large as you scale out.
Great. All right. Well, I think we've had a look, and as always with storage design and storage performance, we scrape on the surface and don't go as deep as you can go. Do check out Michael's book. It should be available now through VMware Press.
That's exactly right, through VMware Press.
What's the title?
Virtualizing SQL Server with VMware, Doing It Right.
And who else was authoring that with you?
So I had 2 great co-authors, Michael Corey, who's the president of Entirety, and also Jeff Sastak, who is a SE manager for VMware.
Excellent. All right, and if people would like to find you some more, where do they find you online?
So I can be found online through either longwhiteclouds.com or at VCDXNZ001 on Twitter.
Excellent. Well, this has been another Notes for Engineers video, and keep coming back to notesforengineers.com to find more videos.